So 3 quick little examples of optimization problems. Um, First one, let's find and classify critical points for this guy. X cubed plus 4x squared minus 11x minus 30. Okay. So to find the critical points, I'm going to set, this is my f of x. So I'm going to set that first derivative equal to 0, and the first derivative is 3x squared plus 8x minus 11. Okay, so that's a quadratic equation, and no obvious roots are jumping out at me, so I'm just going to use the quadratic formula, reminding ourselves what that is. The roots of that equation are given by negative b plus or minus b squared minus 4ac divided by 2a. So plugging that into this equation, we've got a equals 3, b equals 8, and c equals 11. So my roots are x equals negative 8 is my negative b, plus or minus 64 minus 4 times 3 times 11 times negative 11. Okay, so it's 4 times 3 times negative 11. Subtracting that gives me a plus 132 there. And downstairs I've got 6. That turns out to be negative 8 plus or minus 14. Ended up with 14 squared into that radical there, divided by 6. And so my roots are negative 8 minus 14 is 22/6. That's 11/3, negative 11/3. And negative 8 plus 14 is positive 6 divided by 6 is 1. Okay, so these are my 2 critical points. And then to classify them, looks like a pretty easy second derivative to take. I think that's what I'm going to do. So second derivative of the first derivative is, so I'm looking at the first derivative and taking its derivative to get 6x plus 8. Evaluating that second derivative at my first critical point, 11/3 is negative 22 plus 8 is negative 14. The most important thing, the only really important thing about it is that it is less than 0, which means that x equals negative 11/3 is a local max. And I'm going to do this, so I've done that for one of my critical points. Now I'm going to classify the other one here. Plugging 11 to my second derivative. So I'm plugging in 1 to my second derivative here, because 1 is my other critical point. I get 6 times 1, 6 plus 8 equals 14, greater than 0. And that implies that x 1 is local min. Okay, so it's really got this kind of mechanical feature to it. Take the first derivative, set it equal to 0. Find the values of x that solve that equation. For each of those values, classify them using one of the methods. And with polynomials like this, where the derivatives are getting successively simpler as you take higher and higher of them, taking the second derivative and just evaluating it at the point is a pretty easy way to solve the problem. Okay, so let's just do another kind of math book type problem here. Another one where we're gonna find and classify critical points. But now my function that I'm interested in is this one, log of x plus 1 over x. So, you know, where we have logs, we want to remind ourselves that the domain is not the whole real line, it's just the positive numbers. And even without the logs, we'd be noticing that this function wasn't defined at x equals 0 without the log ruled that out as well. Okay, so we're only looking for the critical points that are in the domain of the function. Just as before, I'm going to find those critical points by taking the derivative. So the derivative of the log is 1 over x. The derivative of 1 over x, I'm going to think of that as x to the negative 1 power. So it is negative 1 times x to the negative 2 power, right? The power rule, when we apply it to negative exponents, those negative exponents are getting bigger. So I get 1 over x minus x squared. This is my first derivative, setting it equal to 0, and solving. To some extent, you can just look at it and see that x equals 1 solves it, or you could bring the negative 1 over x squared over to one side and multiply through by x squared. Either way, we've got one critical point here that solves that. And again, I think I'll just go ahead and take the second derivative here. Second derivative is negative 1 over x squared. Now we're subtracting the derivative of 1 over x squared, and so that is this negative times the negative 2 here. Maybe I'll just write out that process, minus the derivative of this term is negative 2x to the negative 3 power. What I was starting to just explain in words, it's easier to show, is that the two negative signs will cancel out, and I'll get negative 1 over x squared plus 2 over x cubed. And look what I did. I did a bad thing. Right here, I kind of double, I did the same thing twice. I can either remember that it's x to the negative 3 power, or I could put it in the denominator. I don't want to do both of those things. So this derivative is to the third power. Just to make sure you see what went wrong for me there, I was taking the derivative of this first derivative, okay, which I'm going to rewrite as x to the negative 1 minus x to the negative 2, and that is negative x to the negative 2 minus negative 2 x to the negative 3, which then equals negative 1 over x squared plus 2 over, once I put the x cubed in the denominator, I lose the negative sign. And so that was what I was fixing right there. Back to our main point here. Why were we taking that second derivative? Because we wanted to see what sign it had at our critical point of x equals 1. So let's just put that critical point right in. Second derivative evaluated at x equals 1. That is negative 1 over 1 plus 2 over 1 is 1. That is greater than 0. So x equals 1 is all right, so one last example, and this one is going to be have less algebra in it and just more of a kind of a general frame for a lot of maximization problems. Okay, so this is kind of the workhorse from neoclassical economics, maximizing profits. I'm a firm and I want to choose the quantity I'm going to produce to maximize my profits. And what are my profits? It's the difference between revenue, which depends on the quantity I produce, minus cost, which also depends on the quantity. And do I need to come up with some fancy polynomial to describe revenue and cost? No, I don't need to do that. Really, all I need to do is talk about the first two derivatives of these things. So what we're going to assume is that the first derivative of revenue is positive. The more you make, the more you produce, the more money you bring in. We're also going to assume that the second derivative of revenue is 0. Okay, so I'm like just a little tiny old firm, and I can sell everything that I make at exactly the same price. So the first derivative is constant. I'm not having any kind of impact, or I don't have any kind of bargaining power or anything like that. Similarly, the more I make, the more my costs, the more I produce, the more my costs are. So this is a positive first derivative. And I'm going to assume here that costs are also increasing. Okay, and kind of the idea there is the first few items that I produce, I'm using kind of my best inputs and my most productive time, and it's all working really well. And then as I try to increase my quantity, I'm having to bring in maybe workers who aren't as good, or use raw materials that aren't as good. So I'm having to pay more to get the same amount of quantity produced. And as we talked about a little bit in the workshop for Unit 5, that's a pretty standard assumption. Not saying it's across the board true, but in the simplest model of how firms make their quantity choices, we usually do assume increasing marginal costs. Okay, and so what is the first order condition here? First derivative, nothing tricky about this one. First derivative has to be equal to 0. So what that is saying is that the first derivative of revenue with respect to quantity has to exactly equal the first derivative of costs. Okay, and in slightly more general language, what we would say at any optimum point is that marginal benefits equal marginal costs. And that is the punchline to many, 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 many optimization problems that you will encounter in social science, especially. How are you at the optimum value for something? The optimum value is the value where the infinitesimally good impact of the last quantity that you produced, the last minute that you devoted to the time, whatever it is, that the marginal good effect exactly offsets the marginal bad effect. Okay, if you're at the point where the beneficial part of what you're doing is increasing faster than the bad part, the costly part, the efficient part, you should keep increasing. If you're at the part where the costs are increasing faster than the benefits, you should make a little bit less. You want to get to the point where the rate at which benefits are increasing is exactly balanced by the rate at which costs are increasing. Okay. So that is, like I say, in one sense, why do you ever need to solve another optimization problem if so many of them have this this outcome? What you might find is that you can actually learn a lot from the thing you're thinking about by figuring out how a situation that isn't exactly as simple as a firm making something and selling them at a fixed price, some other situation where somebody is trading off benefits versus costs, how that exactly maps in to the marginal cost versus marginal benefit framework. Okay, so that's what we have for optimization. You'll have some problems to work, and we'll be on to the next unit. So I'll see you then.